Temperature and kinetics. In this video, we really only have one goal. Explain how increasing temperature increases the reaction rate. So we want to look at kind of the things that we talked about in the last video and focus in on this one idea of why does temperature increase reaction rate, especially according to collision theory and with regards to the activation energy. So I just want to remind you real quick of what we talked about before, that when you're reacting molecules, they have to collide, and they must collide with a certain energy. Now, we said more particles, more likely, and that part makes very easy conceptual sense. More particles, more likely. Now I want to focus on the second part, though. Higher temperatures. That makes it more likely too. But why? Why is it more likely that things are going to collide at a higher energy if we have higher temperatures? Now, of course, the simplest example to this is to say, well, each molecule is going to have a higher kinetic energy on average. And that's true. That's definitely true. It's just a bit of an oversimplification. So let's look into it a little bit deeper than that. So remember back to whichever section it was that you last heard about this. Depending on the class you're in, it can change a little bit. So we know that if we have a sample, whether it be liquid or gas, that the molecules aren't all going to be moving the same speed. There's a distribution of speeds. And we covered this in gas laws, and we covered it in liquids. So you've had it several places now. Now, here I've shown you two different ones. I've shown you a low temperature one and a high temperature one. If you need some more help looking at these distributions, you should go back to some earlier videos or ask for help. We loosely think of these as a frequency table, which is the same idea as a grade distribution. So if that kind of jogs your memory on earlier discussions of it, great. If not, that's fine. Just go spend some time looking at what a frequency graph like this is. So our graphs show our speeds distributions for two different temperatures. And I have a piece of it colored in. And here's what that is. So that E minimum that I have drawn, that's the new thing on this graph. That's the part that you haven't seen before on a graph that looks like this. And what that is that's our minimum energy needed to react. So we've set just sort of a sketch point, right? There's no numbers here, and so it's not any specific thing, but a sketch point saying that at this energy, these molecules will react. Now, if we look at our low temperature graph, so take a second, point to the low temperature graph, trace that down until you hit the E minimum. Now, the molecules that are past that E minimum, look at that tiny, tiny little section of graph. It's hardly any of the molecules. Now, that doesn't mean that the reaction won't happen. It's just that only those molecules that are above that line can react. And so there's very few molecules that have enough energy to have that reaction happen. Most of them are going to collide and go on about their way without ever reacting. Compare that to the high temperature one. So now take your finger and kind of trace the high temperature graph. When you get to the E minimum there, now we have a significant portion above that graph. So instead of maybe 2 to 5% of your collisions causing a reaction like in the low temperature one, now maybe we're at 20% of our collisions causing a reaction. So this allows us to see, in a very useful way using the distribution graph, that there's a difference in speed with regards to the rate of the reaction, and that's related to our rate in our speeds of our molecules, because they have to hit this energy threshold in order to have a reaction. Now, looking at the low temperature one is useful because it shows us why we'll get a reaction even at really at temperatures that are way lower than we would think, because there's a very small percentage of molecules that can still have a reaction. It's just going to take a very long time. And so those are slow reactions.